We'll begin from the current slide. No, I've announced this before in case anyone's interested. This company called STEM Jobs has got this new tool to connect classrooms to careers. It's a company out of Pittsburgh, it looks like. It's called the STEM Type Navigator. Of course, STEM is science, technology, engineering, and math. So it sounds like a pretty good thing. I don't know why we're advertising, but we are. And both of you are transient students, so you won't care about the Lawson Math Club or team. Any questions before we get started today? All right. We're in Chapter 4, which are higher order differential equations, and we're in 4.1, which is the preliminary theory linear equations. Okay? We had just introduced last time superposition principle and with the theorem, homogeneous equations, and then a couple of corollaries to the theorem. And then the example that follows those is where we were going to pick up today. So no questions up to that point. Okay. Here are a couple of functions. Let me get my pen set up. Well, there we go. Y1 is equal to x squared. Y2 and yes, no. You did get the first test, right?
Exactly.
Okay. And the second test, did you get that? Okay, I'll get that to you now then. Okay. Here's test 2. Good deal. All right. I didn't want to get it right. Okay. And here's y2 is equal to x squared log x. Okay. Now, their claim is both are solutions to the homogeneous linear equation x squared. My eyes are not good. Y triple prime. No, that's x cubed. As I said, my eyes are not good. Okay. I can't get the pen to come back. Y triple cubed minus 2xy prime plus 4y is equal to 0. Okay? And this is, they say, is true on the interval 0 to infinity. All right. Any idea, it is still flickering this morning. I don't know if my bulb's about to go or not. Any idea or opinion on why we would limit it to that interval? Say again? What's that?
If x is 0, x is first and 0.
Okay, I heard something about x equals 0. If x equals 0, log x is not defined, right? And certainly any x negative log x is not defined. So that could not possibly be a solution for anything that included either 0 or any negative number. Now, there's nothing that tells us that everything there will be, but they're telling us that. Okay, now, they say that these two solutions, or these two functions, are solutions of this differential equation. Let's verify that. Shouldn't take too long, should it? If y prime is equal to x squared is a solution, what would we do to verify it? Take a derivative. y1 prime would be 2x, and y1 double prime would equal 2, and y1 triple prime would be 0. Okay? Now, let's plug this back in. That'll be x cubed times 0. Well, that's going to be 0. Minus 2x, and y prime would be 2x also. Plus 4y. Well, but y is x squared. So let's go on and plug that in. The question is this equal to 0? Well, this is minus 4x squared plus 4x squared, and sure enough, that's equal to 0. Okay? So y1 equal x squared, that would be good on any interval. Any interval. You're not limited to this. Okay, let's do the same for y2. I'll take a little more effort here. What is y2 prime? Okay, now we've got a product rule. So what would be y2 prime?
In the denominator, what does it say?
Say that again.
Oh, what's in the denominator? NX?
What denominator?
Of like y2 x squared over. Yeah.
There is no denominator yet. There's going to be.
Okay. Oh, is that an ln of x?
Yeah, that's ln of x.
Oh, okay.
Oh, I'm sorry. Yeah, making fun of my writing. I'm not hurt at all. Yeah, I'm okay. All right. All right. What is y2 prime? Use the product rule. Help me, help me. X squared over x plus 2x log x. Okay? I can clean that up just a little bit. This x and one of the x's goes away. So that's going to be x plus 2x log x. Okay? Now we need to do y2 double prime. Okay? I think I'll move this over so it'll be easier to see. But maybe it'll be harder to deal with later. Y2 double prime would then be what? One plus 2x over x. Is that what I heard? Okay. Plus what? 2 ln of x. Okay. Got it. And I'll clean that up a little bit. So this simplifies to be 1 plus 2 would be 3 plus 2 log x. Okay. Now we'll do y2 triple prime because we have that over here. And what would that be? Anybody? 2 over x. Okay. Now let's plug and chug with that one and see what we get. I think I can erase these because it's just getting a little crowded here. So let's get rid of these. We've already verified that one works. Okay. And let's see if this one works. Okay. So we would have x cubed times 2 over x, right? y2 triple prime would be 2 over x, so that's it. So this x is going to wipe out one of those and leave us a 2x squared, minus 2x times y prime, and y prime is x plus 2x log x, right? There's your y prime up here, okay? Plus 4 times y, and our y2 here was x squared log x. Okay, the question is that equal to 0. All right, so here what we have is a 2x, and here a 2x squared, sorry, 2x squared, and here we have a minus 2x squared, fantastic, and here we have a minus 4x squared log x, when you distribute that, right? And here we have a plus 4x squared log x, and sure enough, those two equal 0. These two add to 0, these two add to 0, absolutely. Okay, so here we have two functions that we have just shown do satisfy that third order linear differential equation. Okay, so we didn't have to verify it, but that's not a bad idea to do. Okay, so let's get rid of this. We verified this. It's all true. So let's move on. Okay, and do what the problem actually asks us to do. Okay. By the superposition principle, which we just did in Theorem 4.1.2 last time, it says that the linear combination, since these two are solutions to that differential equation, then the linear combination of them is also a solution. So y is equal to some C1, arbitrary constant C1, x squared, plus some other arbitrary constant C2 times x squared log x, okay, is also a solution on this interval, okay? Now, there's a part of me that says we need to verify this too, okay? There's a part of me that really doesn't want to, okay? But let's think about it for a moment. In fact, it's not that hard to do. It's Monica, right? Okay. We're on example 4, top of page 123 in section 4.1, chapter 4. Okay? So let's do it pretty quickly, if we can. Y prime is equal to 2c1x plus, and it doesn't matter which order you do, 2c2x log x. I did write this right, didn't I? Yeah, okay. Log x plus c2 x, I believe it is, isn't it? No. Yeah. It would be x squared over x, which is x. Okay? There's your y prime. Y double prime would be 2c1 plus 2c2 log x plus 2c2, because x over x, plus c2. Okay? I think we can simplify that a little bit to get 2c1 plus 2c2 log x plus 3c2. Okay? And y triple prime would then be, that goes to 0, that goes to 2c2 over x. Yeah, 2c2 over x. All right. Then if we plug these in, we get x cubed times that would be 2c2 x squared. Okay. Minus, go up to this one, 2, let's make that 4c1 x squared. Okay, I'm multiplying the 2 here by the minus 2x there. I mean 2, sorry. Got lost what I was doing. Okay, minus 2x times a 2c1x would be minus 4c1x, and then a plus. Goodness, this is so easy to get lost here. Oh, it's probably not a plus, it's a minus. Okay. Gag. Okay. We've got a minus 2x here and a plus 2, so that's a minus 4c2x squared. Okay, log x, and then a minus 2x times c2 x would be a minus 2c2x squared. I think I got them all in there, okay? Then plus a 4y, where this is your y, so that'll be plus 4c1x squared plus 4c2 x log it. No, sorry. Excuse me. Sorry. Y'all awake yet? Okay. Just making sure. Okay. Wow. C2 x squared log x. Okay? The question, is that equal to 0? Well, here's a C2 x squared. There's a minus 2c2 x squared. Here's a minus 4c1 x squared. There's a plus 4c1 x squared. There's a minus 4c2 x squared log x, and there's a plus 4c2 x squared log x. Sure enough, that also is a solution. Those two are solutions. Any linear combination of those is also a solution. And notice here, the C1 and C2 are completely arbitrary. Any number you choose to put in there, okay? Including, by the way, 0, 0. Because if you look at this, if y is 0, y prime is 0, y triple prime is 0, so 0, the trivial solution also satisfies that. And we get that by C1 and C2 both being equal. All right, now, I kind of don't like what they did to you here. And they did it without comment. They only produced a 2-parameter system. Don't we know this has to have 3 parameters? Okay? So there's some other solution out there whose linear combination will also work. They only gave us 2 of them. But this one we know, because it's a 3rd-order differential equation, you'll have at least 3, or you will have 3 independent arbitrary constants. We just don't know what they are now. Any questions on that? All right, sorry about the sneezes. Goodness gracious. All right. Here's another. The function y is equal to e to the 7x is a solution, they claim, of y double prime minus 9y prime plus 14y equals 0. Notice these are, when the differential equation is equal to 0, what do we call it? Like milk. Yes, homogeneous or homogeneous, exactly. Okay? Now, let's check and see if that is indeed a solution. What's your y prime? 7e to the 7x. And y double prime? 49e to the 7x. Let's plug those in. 49e to the 7x minus 9 times y prime, which would be 63e to the 7x, plus 14e, because the y is e to the 7x, okay, is that indeed equal to 0? Well, if you add 49 and 14, sure enough you get 63 minus 63. Yes, that is a solution. Okay? Now, because that differential equation is linear and homogeneous, then the constant multiple y is equal to c e to the 7x would also work. And it's real easy to see that one, because if you put a c in here, that just puts a c in there, and that puts a c in here. And then the c goes here, and here, and here, and still everything adds up. So yeah, that is also a solution. Any constant multiple. Now again, second order linear differential equation, and yet they only gave us one parameter. We know there could have been two. There are two somewhere out there. Okay. And for instance, they plug in a few different values for c. When c is equal to 0, of course this is 0, and that works certainly. When c is equal to 1, we've just seen that. That works. We did that first. Any value c you put in there will certainly work. Okay, they do 9, 7e to the 7x, and negative root 5e to the 7x. It doesn't matter what you do, any value for c. Now, new topic, but it's related, very much so related. This is the idea of linear dependence and linear independence, okay? And these are basic to the study of, and by the way, we're talking about linear differential equations. Chapter 4 is higher order differential equations, but A 4.1 is linear equations. So we're only focusing on linear equations here. And not all of you, I guess, have books, or I don't know if you do. Here's what definition 4.1.1 is. A set of functions f1 of x, I put 2 commas in there, okay. f2 of x, f3 of x, comma, dot, 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 up to, do they call it n? Yeah. fn of x. Okay, set of functions. Said to be linearly dependent to begin with. Dependent. Okay? On an interval I, okay, if there exist constants C1 to Cn, okay, not all zero. Some of them can be zero, but not all of them. Okay, such that, okay, C1 F1 of x plus C2 F2 of x plus C3 F3 of x plus dot 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 plus C sub n F sub n of x is equal to 0. Okay? Now certainly that would be true if all the C's were 0. So we exclude that. That's ridiculous. There's no reason. But if you can come up with any set of C's that when you multiply them by those functions, you wind up with 0 as a solution, you know, some linear combination of the functions with those constants. If you can find even one set of C's that's going to make that true, this is a linearly dependent system. Okay? This linear dependent set of functions. Okay? Now, that being said, and this is for every x in the interval. Okay. It has to be true for every x. No matter what x you put in there, that linear combination is going to make that equal to 0. If that's the case, this is a linearly dependent set. Now, if, however, the set of functions, okay, is not linearly dependent, and this is such an incredible statement here, not linearly dependent, okay, on the interval, it is said to be linearly independent, okay? Independent. What a surprising result, okay? Now, a lot of blah, blah, blah. Okay, what's the practicality of this, okay? Well, if this is indeed, and here's Rod. Okay. I didn't ask everybody, but did everybody get a copy of test 2? I think they did. Okay. All right. This is going to be a pretty important result and situation here for linear equations, linear independence or dependence. Independence means there's not any set of C's that will make this set of functions equal to 0 unless all the C's are 0. If there's any set that not all C's equal to 0, any set that does make it equal to 0, then that's linearly dependent. Okay. So the other way to express this, and I think I just said it, is if for this to be true and they're independent, the only way that can be true is if every C is equal to 0. Okay? That's what their next statement here says. I already said it, but just wanted to make sure. Okay. What if we had two functions? Okay, I'm going to go to a clean page here. We're on page 123, section 4.1, chapter 4. Okay. Let's say we have two functions, f1 of x and f2 of x. Okay. If the set of functions is linearly dependent on an interval, then there exists some constant c1 and c2 that are both not zero, such that for every x in the interval, c1, so if these are linearly dependent, then there's a c1 and a c2 such that c1 f1 of x plus c2 f2 of x is equal to 0. Okay? And these c1 and c2 not both 0. Okay? Now, with two functions, these are really easy to pick out. Okay? Make up a function. Name a function. Any function you want to do. Okay. Okay. Let's call this f1. What is it? No, a function, not a differential equation. Just some function. Say again. Y is equal to x. Okay? Yeah, there's a function. It's called the identity function. Okay? Now, for this, some other function, f2, to be linearly dependent on that, it must be some c times x also. A different function, but something multiplied by it. So now we can take this one, pick minus c, add to this one, to that one, we get a 0. Okay? With the functions not being 0, but by a choice of variables. Okay? That's pretty obvious. Okay? If you have a multiple of a function, it's going to be dependent on each other. Okay? Because they're just multiples of each other. Okay? And that's always going to be the case for two functions. Okay? Another way we could say this, if c1 f1 of x plus c2 f2 of x equals 0, okay, then we can say, well, let's solve for, which one do they solve for? F1. Let's subtract c2 f2 of x from both sides, okay, and that gives us c1 f1 of x is equal to minus c2 f2 of x, okay, and then divide both sides by c1. Now we're assuming c1's not 0, okay, and now what we have is f1 of x is equal to minus c2 over c1, with c1 not being equal to 0, f2 of x. So basically, what are we saying? F1 is a multiple of F2. That's what it's saying, because these are just constants, with C1 not being equal to 0. So for two functions, it's pretty obvious. If one is a multiple of the other, they're linearly dependent. But if they're not multiples of each other, probably they will be linearly independent. Now, for three and more functions, not nearly so easy to see. Two is really, really easy to see. Okay? Now, okay. what if, I'm going to go clean page here. Okay. What if this is your F1? Okay, now remember we're talking about linear equations, but not necessarily linear functions, of course. Okay. If your F1 is, I lost it, sine 2x. Okay. And F2 of x is sine x cosine x. Okay. Now on the surface, they don't look like they're multiples of each other, do they? That one has sine and cosine in it. This only has sine in it. So they're obviously not simple multiples, you would think, of each other, unless you remember your double angle formula. And what is it? 2 sine x cosine x. Yes, they are multiples of each other. The C2 could just be the number minus 2, and then you add them together and you get 0. Okay? For any combination of, if you can come up with a set of C's, not all 0, that can make it equal to 0, linearly independent. Okay? Now, how about this one? F1 of x is equal to x, Curry's choice earlier, and F2 of x, I can't write, F2 of x, let me clean that up some. Okay, is equal absolute value of x. Okay? Now, and we're going to do this on minus infinity to infinity. Okay? Is there any way that you can make those two, some linear combination of those, equal to 0? Okay? Well, because this function is x for positive x and negative x for negative x, where x is negative. Warren is here. We're one person shy of perfect attendance. We're missing Taylor. Okay. 2, 3, 4, 5, 6, 7. Okay. If we could come up with any linear combination to make that true. Okay. Now, you sure could if you went from 0 to infinity, no sweat. Or negative infinity to 0, linearly dependent. But from this, no way. Okay? If you chose a minus 1 there, it would be linearly dependent on the right, but not on the left. If you chose a plus 1, it would be linearly dependent on the left, at 0, but not on the right. There is no set of constants that will make that always equal to 0, unless both constants are 0. Okay? Now, okay, there is something they sort of sneak in here. Okay? The other way of phrasing this is if F2 of x over F1 of x is equal to a constant. Now this only works for two equations, two functions, two function system. If that's a constant, then linearly independent. If that ratio is not a constant, it's not linearly independent. Okay? It is linearly independent, not. Okay? So let's do example 5. And again, this may be dragging this out. These are fairly simple concepts. Here's one. F1 is equal to cosine squared x. Okay. F2 is equal to sine squared x. Okay. F3 is equal to secant squared x. And F4 is equal to tangent squared x. Okay. Now, they claim that this set is linearly dependent, okay, on the interval minus pi halves to pi halves. Now, why did they choose that interval, do you think? Could they have chosen a bigger interval? Any ideas? Okay, secant and tangent are not defined at negative pi halves or pi halves. Remember, secant and tangent are both something over cosine. And cosine is 0 at negative pi halves and pi halves, so you can't have anything in the interval for which they're not defined. So no, this is the biggest interval you can have. You can have another one like pi halves to 3 halves pi, or negative 7 halves pi to negative 5 halves pi, as long as they're open intervals and you don't include the endpoints. But no, you can't have anything bigger than that. Okay? Now, how can you show that they are linearly dependent? Okay? Well, just the fact that they're squared trig functions. What pops into your mind right there? How about Pythagorean identities? Well, as soon as I wrote down cosine squared and sine squared, first thing that popped in my mind was sine squared x plus cosine squared x is equal to 1. Okay? And then when I wrote down secant squareds and tangent squared, guess what popped into my brain then? Tangent squared x. Second? Plus 1 is equal to secant squared x. Okay? So guess what? Let's say this is tangent squared x minus, no, secant squared x minus tangent squared x. No, I like it that way. Okay? Okay? Minus secant, where's my pen? Okay. Minus secant squared x is equal to negative 1, right? Okay. Now, with those two facts in mind, then can't I say that sine squared x plus cosine squared x plus tangent squared x minus secant squared x is equal to plus 1 minus 1. Add them together. 0. Guess what? Here's a linear combination of those four functions with a 1 for C1, a 1 for C2, a 1 for C3, but a negative 1 for C4, and that linear combination adds to 0. None of those C's are equal to 0, much less all of them. So that's linearly independent. I mean dependent. Yeah, linearly dependent set. Those functions are tied up with each other like crazy. Okay. Make sense? Okay. All right. So there we did 4 functions. Those just happen to be related to each other very, very closely. Let's talk about some that may not be. A set of n functions, we'll go back to this, f1 of x, f2 of x, f3 of x, dot, 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 up to f sub n of x. N functions here, okay? That is linearly dependent, okay, on an interval I, okay, if at least one of the functions okay, can be expressed as a linear combination of the others. Okay? In other words, if C1 F1 plus C2 F2 plus C3 F3 plus dot 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 plus Cn Fn, if that can't equal 0 for some choice of C's there where they're not all 0, then if that can't be expressed that way, pull one of them out and subtract it from the other side. And now you have a linear combination of all the others. Okay? So this is another way of saying linear dependence. Okay? So their example here, what if you had 3, f1 of x, f2 of x, and f3 of x, okay? And they were linearly dependent, okay? That means there's some set of C's, C1, C2, and C3, that would make that combination equal to 0. Well, if you separated out the f3 of x into some combination of C1 F1 of x plus C2 F2 of x, get talking faster than I can think, okay? Okay, then that's linearly dependent. And if those combination adds to 0, pull this one out, divide everything by F3, or minus F3 if you wanted to, and there you have it. It can be expressed as a linear combination of the other two. And the same thing true with a set of 15 equations. Pull one out, and you can write that as a linear combination of the other 14. But if they're linearly independent, no way you can do that. No way. Okay? Because the only way that could be true in the first place if all the C's were 0. All right. So if you find one function being a linear combination of the other functions in that set, dependent, linearly dependent. So let's do example 6. Any questions before I move on to that? I know this sort of feels like you're beating a dead horse here, but this is something that's going to be important later. Here's a set of functions. F1 of x is equal to the square root of x plus 5. Okay? F2 of x, square root of x plus 5x. F3 of x, x minus 1. F4 of x, x squared. Okay? Now, they say this set is linearly dependent on the interval 0 to infinity. Can you have any bigger interval than that? I think ever so slightly, you could include 0, okay? I believe. There's no reason to exclude 0. You can't include any negative number, though. Why? Square roots. You can't take square root of negative number. So that's almost the biggest you can have it. So let's just leave it as that. Now, so we know the interval's okay, but what we don't know is that, is this how do we show this as a linearly dependent set? Okay? Well, let me just say one thing. That F4 is not going to contribute to anything here. That's independent of the other three totally, because that's a squared term. Okay? Now, so I'm going to leave that one out altogether. Make that C equal 0. That'll be fine, okay, for that C to be 0. But I'm going to look at the other three and see if I can come up with some C1 F1 plus C2 F2 plus C3 F3 that's going to equal 0. Let's see if we can do that. So that'll be C1 square root of x plus 5C1, right? That's C1 F1, plus C2 square root of x plus 5C2x plus C3x minus C3. See if we can come up with that equal to 0 for any arbitrary selection of, well, for some selection of the C's. Okay? Well, the next thing I'm going to do is combine like terms. Okay? Here we have a C1 root x plus C2 root x. And if this whole thing is going to be 0, that certainly has to be 0. Well, that implies that C1 is equal to negative C2, right? Would have to be, right? Yay or nay? Okay with that? Okay, let's take our x terms. This says that 5C2x plus C3x also would have to be 0. If that thing's going to be 0, so that indicates to me that let me write it this way, C3 is equal to negative 5C2. Right? Okay, but, okay, we'll come back to that in a minute. And then it also says that 5C1 has the equal to 0. Okay, for that to be 0, oh, I'm sorry, wrong. Okay, constant terms, 5C1 minus C3, okay, minus C3 has to equal 0, which indicates that C3 has to equal 5C1. Okay? Now, as long as you pick these things judiciously, I think we'll be fine. let's just pick a value for C1. No, C2. Pick one. Anyone. Say again? I couldn't hear what you said. Yeah, just a value, any value. 7? Is that what you said? Okay. So C2 is equal to 7. C2 is equal to 7. C1 then would have to be -7, right? Okay. And C2, and then this would be C3 would have to be 5 times C1 would be -35, right? And and we already have said that if -5 times C2 would be -35. So that 3 sets right there is going to make this work, okay? Now, that's not the only one. You could have chosen 1, -1, and -5. Okay, that would have worked. There's a bunch of C's that you can put together, and these would do it. Let's see, L4, no way that's going to be anything. That, if you put a C in front of that, that's going to have to be 0. That's the only way to make that. But you see, one of them, or two of them, any up to, just as long as all of them are not 0, and certainly here, all are not 0. C4 is going to have to be 0 for that set of unknowns. Okay? So, we've just shown that that is not as a linearly dependent set. Okay? Now, we're primarily interested in linearly independent functions, or more to the point, linearly independent solutions of linear differential equations. And here's how you tell whether we've got it or not. A definition here, and I think all of you have had you probably haven't had linear algebra. Some of you may have. Okay. I'm going to introduce you to something else. Definition 4.1.2 is the Wronskian. What a name. Okay. I believe it was named after Joseph Maria Horne Wronski. Okay. Good Irish name, right? No, Polish name. Polish philosopher and mathematician. By the way, if you haven't chosen a paper topic yet, by the way, paper topic here, obviously one of my best classes ever. And how many papers have I got in so far? 0. Okay. They're due by the end of the month, before the end of the month, so please don't forget about your papers. Okay. Here is one potential paper topic. Who was Wronski? How did he come up with this? That would be another one. How is it used? You know, other applications. I mean, whatever. But that's just one. There's lots of other things you can choose from. Okay. Now, here's the supposition. Here's the given. Suppose each of the functions, f1 of x, f2 of x, f3 of x, ... up to and including f sub n. Do they still count? Yeah, f sub n of x. Every now and then some books will change the subscripts. I don't know why. Okay, suppose that each of these possesses at least possesses, okay, at least n minus 1 derivatives. Okay, so each of these functions has to have at least n minus 1 derivatives. Okay, now here's what the Wronskian is. It's given the symbol W. It's a function, you might say, of these other functions, f1, f2, f3, dot 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 up to and including F sub n. Okay? And here's what it is. It's the determinant of F1, F2, F3, dot 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 up to F sub n, F prime, F1 prime, F2 prime, F3 prime, dot 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 up to F sub n prime. Goodness, my eyes hurt. F sub 2 prime, F sub 3, I'm sorry, double prime, F sub 3, yuck, what is my problem today? It's a 1 and a 2, not a 2 and a 3. Okay, F sub 1 double prime, F sub 2 double prime, F sub 3 double prime, dot dot dot, up to F sub n double prime, and keep going until you get to F sub 1 n minus 1, the n minus first derivative, F sub 2, the n minus first derivative, F sub 3, the n minus first derivative, dot 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 up to F sub n, the n minus first derivative. Okay, the determinant of that, okay, where the primes denote derivatives, that's called the Wronskian of the functions. Okay, man. Oh, and by the way, all these are dot dot dots. Everything's a dot dot. Okay. Everything continues on down. Now, I'm guessing some of you, is there anyone who's not done a determinant before, especially a big one? Maybe. Are you? You've done them, right? Yeah. Okay. Some of you haven't? Okay. Let's do one. That's just what a determinant is. I mean, what a Wronskian is, it's a determinant. We're going to get to what that is in just a minute. Now, here's the theorem that goes along with this. And I'm going to have to clean the screen because I don't have enough room to write it on here, or else it'll be awfully crowded. So let's let y1, y2, y3, dot 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 up to y sub n be in solutions of the homogeneous linear nth order differential equation homogeneous linear nth order differential equation. Okay. On I. Okay. Now this is the equation we had way back earlier. Same one. Differential equation. Then the set of solutions, that's your given. Then the set of solutions, okay, is linearly independent, okay, on I, if and only if. Now here's the shorthand for that, if and only if. Another shorthand for it is the double arrow. One thing implies the other, but the other implies the one. If and only if the Wronskian of those functions, y1, y2, y3, dot 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 up to y sub n, is not equal to 0. Okay? That determinant is not equal to 0 for every x on the interval I. Okay? The requirement is the Wronskian cannot equal 0. Okay? Now, the reason for that is that the determinant of a independent system, of a dependent system, is always going to be 0. Okay? Now, I'm sorry I erased the what that determinant was again. wanted to point out to you also, determinants can only be taken of square matrices. So remember we had y1, y2, y3, y4 up to yn. So we had n columns. And you had the y's, the y prime, the y double prime, the y triple prime, the y fourth prime, up to y sub n minus 1. Well, that is n rows too, because that first row was y to the 0, 1, 2, 3, 4, 5 derivatives. So yeah, that is a square matrix, okay? And that Wronskian cannot equal to 0 because if it is, you got linear dependence, okay? Now, let's do the very easy one. And this is not all that easy, okay? It follows from this theorem, before we get there, that when those are n solutions on an interval, the Wronskian is either identically 0 or never 0 on the interval. Thus, we can show that the Wronskian not equal to 0 for some x0 in I, then the solutions are linearly independent on I. Okay, so here's what we got: y1 of x. We'll start with a simple 2 by 2. Okay, cosine of 2 log x. All this looks really simple, doesn't it? Okay, over x cubed, and y2 of x is sine of 2 log x over x cubed. Okay. Now, it's telling us that these two are solutions of this differential equation. Okay. X squared y double prime plus 7xy prime plus 13y equals 0. Homogeneous or a homogeneous linear second order differential equation. Okay? Now, my solutions, that's an ugly looking combination there. Let me, oops. Okay, solutions. Okay. Now, I sure don't want to do this, but I think we've got to. Okay. We've got to show that these are indeed solutions. Let's do, okay. Yeah, we've been going more than an hour. Do we need a little break? I know one person did, so let's give a break so he's not. All right. Now, here is our problem. They're saying these two are solutions to that differential equation. Especially with these being such complicated looking things, I think we probably need to verify that, don't you? And it's not going to be too bad to do because we got to do some of these steps anyway. So what the first thing you might try to do? Yeah, take a derivative. y1 prime of x is going to be, oh boy, what have we got here? Okay. Say again? Okay, it's certainly going to have a sign. What I'm going to do first, because I really don't care that much for the quotient rule, it's a nice rule and everything else, I want to rewrite this as x to the minus 3 cosine of 2 log x. That way I get to use the product rule. I like that a little better. It's a little bit simpler. Okay? So, what's your y1 prime? And you can use quotient rule if you want to, or you can use product rule. You got them both there, either one you want. How does that go? A little louder? All right, negative 3. Oh, wait. You're doing quotient rule? No, you're doing product rule. Well, then that would be a minus 3x to the minus 4, wouldn't it? Okay. The power rule, which is what we're using here, exponent times coefficient, that's minus 3. X to the drop that by 1, minus 3 minus 1 is minus 4. Okay? That's where we begin. Times the second one, cosine of 2 log x. Okay? That's the first term. Second term is plus x to the minus 3, the first one, times the derivative of the second, which is what? Derivative of cosine is, and that's where your sine came in, right? What's the derivative of cosine? Negative sine. A negative sine, okay? So I had to change that to a minus then. Sine of 2 log x. But then we have chain rule, okay? And derivative of 2 log x is 2 over x. So we'll have a 2 here and another x in the denominator, which brings this up to minus 4, right? Because that would be over x cubed, and then another one would be x to the 4th. Well, what does that turn out being? Okay? It looks to me like that turns out being a minus cosine 2 log x plus sine, okay, I'm sorry, 3 cosine 2 log x minus, plus 2 sine 2 log x, okay, over x to the 4th, okay? Now, I didn't have to go back and write it that way, but that's how I chose to. See, now what I did was pull out the minus sign from both of them, made the whole thing negative. And this left me a 3 cosine 2 log x up here, and a plus as I pulled out the minus sign, plus 2 sine 2 log x here over x to the 4th. Okay. Now, I'm not saying that's the one I want to use to take the second derivative, but I did want to show you a little bit easier, or I guess a little bit easier, simple way to write it. Now, when we go to take the second derivative of this, that'll be y1 double prime of x. I want to go back and use this one because that's the one I want to go by. And I'm going to clean this up just a little bit so it'll be easier to read. That's to the minus 4. Okay. Again, I like product rule better than quotient rule, so if I can, I usually change them like that. Okay. You don't have to. That's just my preference. So what's y double prime? Help me, help me. And again, I would use this one to take the derivative, but that's me. If you like the other one, use it. 12 to the negative 5 times cosine 2 log x, okay, plus okay, all right, you're doing plus a negative 3. What I'm going to do, when you said plus, I wrote it down quickly because, you see, that's going to be a minus, but then the derivative of cosine is going to be minus 2, so that's why I wanted a plus there. All right, so I'm going to leave it a plus, okay? And that will be, say again? Okay, where'd you get the 5? Okay, so yeah, all right. This is the derivative of the first times the second, plus the second times the derivative of the first. Okay, wait a minute. No, I said it backwards. We did derivative of the first times the second. That's that one. Now we do the first times the derivative of the second. Okay, so that's going to have a 3 from here. So I'm going to put the 3 here for now. Okay. And the x to the minus fourth is going to stay the same because it's the first, times the derivative of the second, which is going to be the minus sign, so that's what changed it to a plus. So that'll be a sine of 2 log x, right? Right? Times 2 over x. So that will make this a 6, and that makes it x to the minus 5 again. Okay? Is that right? Okay? I'm sort of cheating a little bit. Okay? Now let's do that second part. And that will be that's a 2, and that's minus 4. So that's going to be a plus 8x to the minus 5 sine 2 log x, right? Now this will then go back to being negative, right? Because that's going to be a 2x to the minus 4, and derivative of sine is cosine of 2 log x. I'm running out of room fast. Times 2 over x. So that's going to make that a 4 and that a minus 5. Okay. All right. Let's see what we've got now. Okay. Who wanted to do this anyway? Whose idea was it, huh? Okay. But you see, coming up here, you have, this is a 12 cosine 2x, and here we have a minus 4. So that's going to leave us an 8 cosine 2 log x, okay, over x to the 5th. But all of them are going to be over x to the 5th. And here we have a plus. Here's a 6 plus 8 is 14 sine of 2 log x. Okay? And all this is over x to the 5th. That's the shorthand way of writing that one. All right. Yuck. Let's plug this in and see if this works. X squared times this one. Of course, this x squared is going to wipe out the 2 of these, and that's going to leave you over x to the 3rd. Okay? So that would be 8 cosine 2 log x plus 14 sine 2 log x. All that's over x to the 3rd. Okay. Plus 7x y prime. Well, your y prime was x to the minus 4. The x is going to make that. So this is going to be, I'm going to go back and make them minuses again. This is going to be a minus 3 cosine 2 log x and a minus 2 sine blah blah blah. Okay, and that's over x cubed, and then 13 times y, there's your y up there, that's plus 13 cosine 2 log x over x cubed. So everything's over x cubed. All right? Well, let's see what we've got now. Okay? We got a mess. Don't we? It doesn't look like it's adding up right, does it? Here we have 8 cosine minus 3 cosine. That would be 5 plus 13 is 18. I've messed up some signs somewhere here. Sorry about that. Whose idea was this anyway? Okay. Oh, I'm sorry. I forgot my 7. That's where I messed up. I think that's going to help some. Okay. I forgot the 7 there. That's going to make minus 21 and minus 14. I'm sorry. That's one place I messed up. Minus 21 and minus 14. Okay. And that sign is all that same stuff. Okay. Now let's go back and take a look. All right. 8 and 13, 21 minus 21, that's 0. And this is plus 14 sign, minus 14 sign, that's 0. It does work. Okay. Now, as most good math books, and certainly math professors say, we'll leave the other to the student, okay, to do, right? To try that second one. It's going to work out the same way. When you do the sign here, you're going to wind up the same procedure, same way. Your sign, your SIGN signs are going to work out. Everything's going to be fine. And you'll wind up with the same result. Okay? It'll be 0. Now, the question here is, are these functions linearly independent? Okay, we're going to say both of them solve this differential equation. I showed you one, you can do the other. It's not going to be that much worse. Okay. Now, I'm trying to figure out why they start mentioning these functions here, the coefficient functions. Note that the coefficient functions a2 of x is your is the x squared right here, and a1 of x is 7x, and a0 of x is 13. Okay? They're all continuous on 0 to infinity, so everything's good there. And the a2 of x is not 0 for every value of x. Okay? Only, in fact, it's 0 for none of the values. Okay. Now, what we need to do is do the Wronskian. Okay? Now, some of this we need and some we do not. And I'm trying to find my eraser here. Okay, we need the y's. And we'll leave it in that form. Okay, and we'll, yeah, okay to do that. And we need the y prime. Remember, you do y to the n minus first derivative of y. And since it's a second degree differential equation, we need the first ones. So I'm going to leave that. Here's the one we do need. And I'm going to leave that in that form. We don't need the y double prime. We did for showing the equation work, but we don't for the next part. And I can't tell what these things are. I hope I'm not erasing the wrong things. Okay. We needed the first derivative of each of those. Okay. We only got the first derivative of that, and we need to do the first derivative of the second one. Okay. And that's not going to be too bad. Let's rewrite this as x to the minus 3 sine of 2 log x. Okay. And let's do y2 prime. Okay. I like to use that one. Start it off for me. First derivative of this. Anybody? A little louder. Negative 3 x to the minus 4 sine of 2 log x. Okay. Okay, this time it's going to be a plus because the root of sine is positive cosine. Okay. Plus. Okay, let me just go and write down x to the minus 3 cosine of 2 log x. But then when we do our chain rule, what does that give us? 2 over x, which is going to bring that up to a minus 4, right? Okay, so let's rewrite this as, I'm going to put the cosine in front because it's positive. 2, yuck. Okay, 2 cosine 2 log x, okay, minus 3 sine 2 log x. Goodness gracious, my writing stinks, okay. That's really ugly. Let me see if I can clean that up some. I can't even read it. No, that's not too bad. Okay. Okay. No, that's the wrong place. I'm saying, no wonder it didn't look too bad. I erased the wrong one. Okay. Okay, log x. Okay. And all this is over x to the 4th. Okay. So, we got our functions and our first derivatives. What we need to do is the Wronskian. And now I'll show you how to do a 2-by-2 determinant. The Wronskian of these functions, y1 and y2, is going to be the determinant of y1, that's cosine 2 log x over x cubed, sine 2 log x over x cubed, over the derivatives, which really stink here. I think I'll go back and put the minuses in. Minus 3 cosine 2 log x minus 2 sine 2 log x, sorry, it's getting awfully cramped here, over x 4th, and this is, there it is, 2 cosine 2 log x minus 3 sine. Okay, and that's going to be over x to the 4th. Sorry about this. Really cramped and crowded. Okay. Here's how you do a 2-by-2 determinant. Tell us. It's this product, the main diagonal, minus the product of the anti-diagonal. So multiply these two and subtract the product of those two. Okay. So that Wronskian is going to be, let's do this product this way. That's a cosine here, a 2 cosine there. That's going to be 2 cosine squared 2 log x. That's the first term. And then this one times that one is going to be minus 2. That's a 3. I can't read my writing. I think that's a 3, isn't it? Yeah. Minus 3 cosine 2 log x sine 2 log x. Okay? And all those are over x to the 7th. Okay? Minus, and we're going to do this product. And that's a minus times a minus, so that's going to be a plus 3 cosine 2 log x times sine 2 log x. Okay? And then the other plus 2 sine squared 2 log x. And all that is also over x to the 7th. Okay. Now, yuck. This term is a minus term, and that term is a plus term, and they're identical. So those add to 0. These, however, are 2 cosine squared of that plus 2 sine squared of this, all over x to the 7th. Well, that's going to be 2 times 1, right? So it would be 1 over x to the 7th. No, I'm sorry. 2 over x to the 7th. Okay, now that's take some looking to see. These two, I hope you see those two. This is plus minus 3, that's plus 3. Those go away. Same terms over x to the 7th. These are 2 cosine squared 2 log x plus 2 sine squared 2 log x. Well, it's 2 times some of that. And some of that is 1. Sine squared plus cosine squared is 1. So it'd be 2 over x to the 7th. And guess what? That is not 0 on that interval. Okay, did I lose my interval? I'm afraid I did. The interval was from from 0 to infinity. That's never 0. Ever 0 anywhere on that interval. Okay? Now, I may have done something wrong here. I got x's to the 4th in the denominator. They got x's to the 6th in the... Oh, that's because they left x squared up top. Okay. Silly of them. Okay. Now, and they did something else that's bizarre. They just chose x equal 1. All it had to be for any x in the interval, and x equal 1 would work, and that would be 2 then. The Wronskian would be 2. All we're interested in is that the Wronskian is not 0, and that one can never be 0, so we're okay. These are linearly independent solutions of that homogeneous set. We showed that one of them was, you could think through and see the other one was, then the only other thing, we had to show they were linearly independent. We did using the Wronskian. Okay. Now, whoa. we're basically right at the end of time. Let me, didn't sound good, did it? We'll pick up next time, okay? And with definition 4.1.3, okay? I was going to say let me go on and just save that one, but let's not. Save that for lead off for next time. All right, homework exercises here. I think you can do any of the odds 1 through, either 1 or 3 or both. Those answers are in the back. 5 or 7 or both. Those are in the back. Do number 9. Do number 11. Do number 13. And let me see. Do any of the odds 15 to 21 and stop there. This is on pages 130 and the top of 130, very beginning of 131. Okay. All right, good deal. And we'll pick up and go from there. Okay. I promise you it's going to pick up a little bit. These first sections in every chapter are just so dry to me. But there are things you need later on. So once we got these down, I think we'll be able to move along a little bit better. All right, good deal. Have a good, let's see, wait. No, this is only Tuesday. Okay. We'll see you on Thursday.